engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to this week's Naked Scientists. I'm Chris Smith, and this is the programme that brings you the latest breakthroughs and where we talk to some of the biggest names in science, technology and medicine. Speaking of which, this week we're hearing from the atmospheric chemist and expert on the ozone hole, Susan Solomon.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
On today's edition of Titans of Science, we're going to hear from Susan Solomon at the National Oceanic and Atmospheric Administration. Susan is an atmospheric chemist, and she was one of the first people in the world to respond to reports in the early 80s of deterioration of the planet's ozone layer. She joined the faculty at MIT in 2011, where she serves as the Ellen Swallow Richards Professor of Atmospheric Chemistry and Climate Science. She's frequently cited as one of the most important women in science, and in 2008 was selected by Time magazine as one of the top 100 most influential people in the world. Time went on to say, "All scientists like to believe they will leave the world better than they found it. Susan Solomon surely will. Having helped save the Earth's atmosphere already, she's now playing a role in trying to do it again." Well, before we find out how you're doing it again, Susan, welcome to the programme. Pleasure and a privilege to have you with us. The first thing that you did for the atmosphere concerned the ozone layer and a hole that turned up therein. How is the health of the ozone layer now?
Well, the ozone layer is really the world's signature environmental success story. We have already seen the chemicals that were causing the ozone depletion to start dropping, and drop quite a bit. And we've actually seen the Antarctic ozone hole start to get a little bit smaller and form a little bit later, particularly in the month of September. So that's a huge win. It would have been so much worse by now if we had not stopped using those dangerous chemicals.
It's so nice to start a piece like this with some good news that we're going to tell people about. Maybe we'll change that later on. But let's back up very slightly. What is the ozone layer? The clue's in the name, obviously. But what does it do for us and why does it matter?
The evolution of life on this planet wouldn't have happened until the ozone layer actually evolved. So ozone is a form of oxygen that has a somewhat different structure. Instead of having two oxygen atoms together, it's got three. And that allows it to absorb certain wavelengths of ultraviolet light that would otherwise make it all the way down to the ground. And as anyone knows who's ever been sunburned, we really need to be careful about ultraviolet.
Where is the ozone layer?
Most of the ozone layer is located between about 12 and 30 kilometers above our heads. So there's not much ozone in the lower atmosphere. And that's a good thing because ozone is actually quite toxic when you breathe it. You want it up in the upper atmosphere protecting you from ultraviolet, but you don't want it down at the ground in the air that you're breathing. People who had to breathe it in smog episodes, for example, in Los Angeles in the 60s and 70s, or even now in places like India, really do suffer. So we want it up there. We don't want it down here.
And how did it come to light that ozone had a problem?
Well, the earliest work highlighting the idea that the ozone layer might be in danger actually goes back to the mid-1970s when two chemists pointed out that we were using these dangerous chemicals in larger and larger amounts, and the concentrations were building up in the atmosphere, and that they could destroy ozone. So the idea that something could last in the atmosphere for 100 years was critical to that concern. And people began to be concerned that if we kept using these compounds, we might see a few percent depletion or loss of the ozone layer in about 100 years. So it was a small change. It was far in the future. It was kind of a future problem, if you want to call it that. But then in 1985, the British Antarctic Survey discovered the Antarctic ozone hole, which was a huge surprise. We didn't expect to see big ozone losses that early. Over Antarctica, you lose not a few percent, but more like 50% of the total amount of ozone over your head. That protective layer is reduced by a massive fraction. And we didn't expect it in Antarctica. So it was a huge mystery initially.
It was Jonathan Shanklin and Brian Gardner and others who spotted that, wasn't it, that hole?
Yes, and Joe Farman, who unfortunately is no longer with us, but they did some amazing work there. They they managed to show us something that the satellites had not seen, which was quite a shocker to the science community. And the truth of what they said has obviously stood the test of time and then some.
When we say hole, is it really a hole? And how big is it?
Well, it's a 50% loss of ozone. It's not 100%, so that's good news in a way. But the reason that it is 50% is that in a layer between about 14 and 24 kilometers, there is indeed a hole. The ozone is completely gone in that layer. So the half that you have left is only what's above and below that region where it's completely gone. The reason, though, that it began to be called a hole is how dramatically it looks isolated when you look at it on satellite imagery. So the reason for that is that the Antarctic atmosphere, you can think of it as being kind of like a whirlpool. There's literally what we call a vortex, but think of a whirlpool like what you have when you drain your bathtub or whatever. That keeps the air inside the middle of the whirlpool very isolated, and the ozone just gets eaten away and eaten away and eaten away. So it does kind of look like a hole. It's a very big hole. It's twice the size of the continental United States. That's actually
Does it
extremely big.
actually extend beyond the margins of Antarctica?
Slightly, yeah. It's about 25 million square kilometers at its height in a bad year.
So are we just fortunate, in a way, that because of the geography of Antarctica with that polar vortex, that whirlpool, that has concentrated the chemicals that are depleting the ozone down there, and we can perhaps come on to that in a minute, is it convenient and fortunate that it's happened there, where there aren't so many people, just research scientists chiefly and holidaymakers, and not over more populated parts of the planet?
Yes, but I'll hasten to add that we also see significant ozone losses over the Arctic, where there are a lot more people. And we also see now significant ozone losses over mid-latitudes, both southern and northern mid-latitudes. So although the ozone hole can sort of be thought of as like the canary in the coal mine, it showed us first that there was going to be a big problem. And not too long after that, we started measuring bigger changes at other latitudes than what we expected to.
Can you talk us through what the chemistry of the ozone hole is? Because you alluded to the fact there were some toxic chemicals that those scientists pointed out in the 1970s as a possible future problem, that they could be storing up trouble. But what were those chemicals, and what is the mechanism by which they degrade ozone, and why specifically concentrate down in Antarctica?
Most of the problem comes from chlorofluorocarbons. And interestingly enough, these molecules were being used in large amounts in things like refrigeration, air conditioning, foam blowing, and especially as the propellants in spray cans. So back in the 1970s, actually about 75% of the global use of these molecules was in literally hairspray and underarm deodorant of people all around the world. So the idea that it was building up and building up every year, that it had a 100-year lifetime and it might deplete the ozone layers someday, was enough to actually motivate the American public to give up spray cans. So what happened was that hairstyles changed, and people literally went on the stick to save the ozone layer. They started using stick deodorant. And it's also really interesting that this country was really first on that. The American consumer gave up these chemicals before there was even any regulation. And that was mainly motivated by the environmental groups urging people to do that, and people voluntarily did it. So it really shows you the power of public opinion and the power of the consumer on certain environmental problems when you can, in fact, take action. And we can take action on all kinds of things, in my view. But certainly in this case, the action was huge because 75% of the market is a real punch in the stomach to any industry, and the American chemical industry certainly took note of that.
Ironically, in a program talking about atmosphere and air quality, I think even asthma inhalers were using CFCs, these chlorofluorocarbons, to propel the drugs down the lungs of people who had airway problems, weren't they? But I think you're referring to the Montreal Protocol and Treaty of 1986, which led to a massive reduction in use worldwide of these chemicals. But why are they so bad for ozone? Do we understand what they do to the ozone to make it fall apart so we get a hole in the first place?
Yeah, we certainly do. It took us a few years, but actually remarkably only a few years. I think the whole scientific community deserves a lot of credit for being so fast in figuring this out after the British pointed it out. So the way it works is that Antarctica really is the coldest place on Earth. It's so cold that clouds form in the very dry Antarctic stratosphere. So the stratosphere is dry everywhere, and normally we don't have clouds at stratospheric altitudes. We have them down here in the lower atmosphere, but you don't get them where the ozone layer is normally. You get them very, very frequently in the Antarctic and sometimes in the Arctic. It's just much less common to get the frequency of polar stratospheric clouds being as much in the Arctic as it is in the Antarctic. So the coldest place on Earth with all those clouds provided a surface for chemistry to happen that simply doesn't happen when all you have are gases. And that fundamentally changed the extent to which these compounds could deplete ozone. So it's not that there's more chlorofluorocarbon down there than anywhere else. It's just that it's more potent because of this surface chemistry on those cloud particles.
It's also seasonal, the hole, isn't it? We see headlines that this year it's grown, then it shrunk a bit. Why seasonal?
Yeah, that is such a cool thing. So you need not only cold temperatures, but you also need sunlight to drive the chemistry that's involved. And that's a little complicated. The main point is that the air, when it's cold and dark, the chemistry just can't get cranked up. What happens is that the chlorine on the surfaces of these clouds makes a molecule called Cl2, which is actually chlorine gas. It's a very strong absorber of any kind of light, immediately breaks it down, and those chlorine atoms then go on and destroy ozone in some further reactions. But that's why you need sunlight as well as cold temperatures. And then when it gets too warm, the chemistry can't happen anymore. So basically, it's sort of a Goldilocks effect where you need a combination of cold and light, and you get that sweet spot right in the Antarctic in their spring, which I would point out, because it's southern hemisphere, is August and September, not what we would think of like February and March in the northern hemisphere. We do see ozone depletion in the Arctic to some extent in February and March too, but nothing like the Antarctic in almost all years.
You mentioned, and it was a surprise to me because I hadn't heard that before, that we're also seeing ozone depletion at other latitudes, not just down on the South Pole, and you just mentioned the Arctic. If it's down to temperature, that's not going to be the case at these other latitudes so much, is it? So how do we account for that loss?
Well, these surface reactions happen to a limited extent everywhere. And, fundamentally, that's a big part of this. And there's also some mixing of the ozone depleted air from the Antarctic down to, say, New Zealand and Australia. Same thing happens in the Arctic. So there's some communication of that depleted air. And the gases are also doing some loss of ozone. But it is mostly that surface chemistry operating to a more limited degree at warmer temperatures.
How do we expect then that climate change will influence this? Do we think that if we push temperatures up, then this makes things worse in the Antarctic, or will it make things better? So we have to suffer a hotter climate, but we get our ozone back.
Boy, that is a fantastic issue. It turns out that although carbon dioxide and other greenhouse warming agents warm the lower atmosphere, they actually cool in the stratosphere. And so the sign of the impact of increasing carbon dioxide actually flips. And we have great satellite data now that shows unequivocally that we have cooling of the stratosphere that is due to the greenhouse gases. So if anything, that effect would make it slightly worse. It's not big enough to have an enormous effect. And in the Antarctic, you're already way colder than you need to be to make these clouds. So the effect is not large there. Where it might have a bigger effect is actually in the Arctic, because you're kind of right on the edge in the Arctic. So ironically, the fact that climate change agents warm the lower atmosphere but cool the upper atmosphere would actually make the ozone loss potentially worse. Another thing that's come up recently is the impact of wildfires. There's pretty good evidence that wildfire smoke from the Australian fires actually impacted the chlorine chemistry at mid-latitudes over Australia in a way that's surprisingly similar to what happens only at cold temperatures on the polar stratospheric clouds that are normally there. So it's just a different kind of particle that can do different chemistry. It's really amazing how clear-cut the satellite data on this actually are. I think the whole community now is wondering, as we go forward into this 21st century, get a little bit warmer, hopefully before we start to turn it over and stop warming, but we probably will get a little bit warmer, and we are seeing more wildfires. To what extent could that actually affect the recovery of the ozone layer is a very interesting question. So one that I'm actually working on right now.
Why do we still have a hole, though? Because it will soon be 4 decades since it was confirmed and we launched one of the most successful environmental protocols that's ever been launched, that you allude to, that people responded like we've never seen people respond before, and industry too. Why is the hole still there, though? Is it that we're seeing the legacy effect of what damage we did do, and it's just going to take a long time for those chemicals to disappear, or has something else taken over as the source of the toxic chlorine that dismantles ozone?
As was said in the 1970s, these molecules that are causing the problem really do have long lifetimes in the atmosphere. So these chemicals last anywhere between 50 and in some cases even as much as 500 years. The stuff that I used when I sprayed my hair when I was a teenager in the early 70s, some of it is still here. And that's kind of amazing, but that's what happens when you talk about a chemical with a long atmospheric lifetime. So it's still here, chewing up the ozone layer, and makes me think about every time that I do something that produces a long-lived chemical, what really is my impact on this planet?
Even CO2 has a long lifetime in the atmosphere, doesn't it? It's measured in centuries. When you light a match, the CO2 that's coming off the end of that match is going to be around for a lot longer than we are. It's also extraordinary, just listening to what you're saying about the legacy effect of chemicals that hang around for a long time, that really the writing was on the wall for these chlorine-based chemicals, and yet we've gone ahead making what we now dub persistent organic fluorocarbons and these alkyl groups and things, which make plastics feel nice and make our paper so we can put greasy things on it and not get greasy fingers. And they're now being found all over the planet, yet we continue to produce them in prodigious quantities, and it seems strange that we've gone from poisoning the air to poisoning the planet elsewhere.
I am always concerned when I see that we're thinking about things that are persistent, because we've made so many mistakes with them in the past. It's not just chlorofluorocarbons with their 100-year lifetimes. Think about DDT, for example. DDT had about a 20-year lifetime in soils. And people just didn't realize that by using it as a pesticide year after year after year, that building up and causing tremendous damage to wildlife, especially the deaths of the robins back in the 60s were what prompted people to realize that persistent pesticides were dangerous. Nowadays, we're talking about persistent fluorinated compounds, PFAS compounds. And we are lucky in one respect. Fluorine does not deplete the ozone layer, unlike chlorine. So it's not a risk to the ozone layer. But certainly these compounds are, everywhere, and they're building up in our bodies, in the ecosystem. And there's a lot of questions about how dangerous they are. And they'll be with us for a long time. Plastic, of course, is the same problem. Plastics have lifetimes of many hundreds, if not 1,000 years, depending on what kind you talk about. So they do break down to make microplastics and even nanoplastics, but it's pretty frightening how many little pieces of microplastic are in a plastic water bottle. This is all going into our bodies. We don't know what happens to it.
Time magazine said you had saved the planet once. Now you were trying to do it again. Are they referring to the fact that we've moved beyond ozone and we realise that we have a really big problem with carbon dioxide now?
Yes, I had the honor of being part of the Intergovernmental Panel on Climate Change the year before Time magazine cited me, working with 150 wonderful scientists from around the world to produce a report for the world that had the statement, "Warming is unequivocal," as its key finding. Those words, I think, have resonated and are still part of why people are so concerned. The evidence that we are warmer is now so clear that, climate deniers don't really try to pretend that it's not warming anymore. They tried that method for a while. They could get away with it, but that's just not going to work now. Too many observations and people's own perceptions that summers are hotter and extreme heat waves are hotter than they were before in many, many parts of the world. Not everywhere, but in surely an overwhelming number of places. So yes, I've been also involved in climate change. You mentioned the issue of the lifetime of carbon dioxide in the atmosphere, which is also one that I've worked on, and what the implications of that are for warming. And it's really kind of bad news there. Most of it does go away on a time scale of maybe 150 years. So that's actually comparable to the chlorofluorocarbons we've been talking about for the ozone layer. But some of it stays in the atmosphere, about 20% of it actually, for about 1,000 years or more. So every time that you drive your car, or your gasoline-powered car, that is, or as you said, light a match, you're adding stuff to the atmosphere that will be here for a very, very long time and cause warming.
One of the points you made earlier was the huge response from the public and industry to CFC's hole in the ozone layer. Now, that hole in the ozone layer was not going to affect most of the people who reacted there and then, but they did react, and we got one of the most successful treaties ever out of that. Why have we, despite the demonstrable evidence that we have got a climate problem, why do you think we're seeing such a lot of inertia? Is it that it's such a hard nut to crack? Throwing away a few aerosols was relatively easy compared to completely changing our lives because we had become so addicted to a carbon-based source of energy. Is that the reason?
I think that's part of the reason. The other thing is that we're late to the party a little bit here because it wasn't as obvious initially. I think that people become concerned about an environmental problem when two P's are satisfied. They have to think that it's personal to them, and they have to think that it's perceptible to them. So, in the case of climate change, I think people are now recognizing it as a personal risk. Lots of people are dying in heat waves and tremendous damage being done in extreme rainstorms that are worsened because of more water in the air, because warmer air holds more water. So it's become personal, it's become perceptible, but there's a third P that is part of solving any environmental problem, and that is that people have to believe that the solutions are practical. And unfortunately, I think we've been sold somewhat a bill of goods, but also the evolution of this problem has been so fast that it's hard to follow. So people have believed that there is no practical solution, that there's nothing they can do. There's plenty they can do. We never solve any environmental problem until people get together and demand change. So that's one really important thing you can do, even by the simple act of voting, if not even better by participating in groups, or even just, talking to people. Talk to your neighbors, talk to people in your church, wherever you go and meet people. All of that is really important. In terms of personal actions, if you're working and you have investments in your retirement, like a 401k, as we call it, you can take a good hard look at those investments and try to decide which ones you think are good for the planet and which ones aren't. There are many ways to put pressure on industry to change. So what happens, if you don't mind, I'll just say I've written a book about this where I go through a whole series of environmental problems and I show how important those three Ps are in solving every one of them, whether it's lead in gas and paint, or DDT or smog or the ozone layer or climate change. The 3 Ps start us off, and then what we need is technology steering. So what I mean by that is that people's demand for change will motivate industries to make changes. And it will motivate governments to do things that further foster those changes, even if what the governments do is something as simple as funding research to investigate what you can use in a spray can instead of a chlorofluorocarbon, or how good you can do with different types of batteries so that you can use solar instead of fossil fuel energy in your power plants. All those kinds of things are happening because people demanded it.
The one P that people never mention when discussing this, though, must be the P for population. And every person listening to this programme in a Western country has got a carbon footprint of up to 10 tonnes of carbon dioxide per year. And the more of us there are, the bigger that's going to be. But no one mentions the fact that were we to have a much smaller human population, it was not growing at the huge rate that it has, we would have a much smaller problem.
You know, it's so much fun. Every time I talk about the 3 Ps, everybody always wants to add a 4th one. And it's a lot of fun to think about them. The population issue is an interesting one, though. I take your point that the tremendous growth of population of the 20th century has meant that we have a lot of people on this planet, but we're not projected to grow that much more in the future. So, you know, we have on the order now of 8 billion. And sure, it would have been much better if we'd stopped at, 3, but we didn't. And we are where we are. We have 8. The real problem today is that there's about 1.5 billion, maybe 2 billion people living a comfortable, if you will, developed country lifestyle like what we have in the United States and Britain. But there are some 5, maybe 6 billion people out there in the world who really are suffering and don't have they don't have electricity, they don't have toilets, they don't have the kind of healthcare we have. So, that they develop is imperative. I think no feeling person could say that they shouldn't develop. But if they develop using carbon-based energy, fossil fuel energy, the way we did, this planet's going to get very hot indeed. So I'm arguing that it isn't so much the 20%, maybe more people that we're going to have. It's the development of the people that we already have, who right now are emitting per person. I believe the correct number is about 5 times less per capita on average than we do. So you can run the math on that. And what you see is that if they use fossil fuel energy, that's what's going to cause it to balloon. But they're already here. It's not so much future population. You're right that perhaps we shouldn't have let it get to this point, but why did it get to this point? Well, partly it got to this point because we got so much better at growing crops, and so we could feed people more easily. We developed fertilizers. We developed vaccines and healthcare that, even though it's not complete, it at least does something about some of the worst childhood diseases. So survival rates are better. I mean, I don't know how you can be against any of that. What we need to do is learn how to exist on this planet sustainably, all of us.
Our thanks to Susan Solomon. And on the subject of climate change, Titans will be taking a break next week because we will be gearing up for the start of the Summer Paris Olympic Games. And we're going to learn about the extreme conditions that some athletes might have to reckon with in order to be in with a chance of glory. What does competing in 38-degree heat mean for an athlete's physiology? And is pickle juice the anti-cramp elixir? Tune in to find out. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith, and from all of us here on the team, thanks for listening, and until next time, goodbye.